In this video, we are going to look at simplifying cubed roots with variables and exponents. So the key here is we are dealing with cubed roots, not square roots. So for example, let's say we wanted to simplify the cubed root of 54. So it's going to look like this, cubed root of 54. When we're simplifying with cubed roots, we need to focus on what are our perfect cube numbers. And so I've started a list over here. And these numbers are perfect cubes because they are the result of cubing a natural number, or an integer, I should say. They could be negative. I could add the negatives to the list. Actually, I probably should do that. So 1 to the third power is 1. 2 to the third power is 8. 2 times 2 times 2. 3 to the third power is 27. 4 to the third power is 64. And 5 to the third power is 125. And I could keep going. But I kind of skipped down to 1,000, which is one that pops up once in a while, which is 10 to the third power. Now, like I said a second ago, we could have negatives as well when we're dealing with perfect cubes, which is something you can't have when you're dealing with perfect squares. Because if you square a negative number, it's always positive. But if I take negative 1 to the third power, I'm going to get negative 1. So negative 1 is a perfect cube as well. If I take negative 2 to the third power, I get negative 8. Negative 3 to the third power is negative 27. Okay, so negative numbers, you can take the cubed root of negative numbers. For example, if I were to then ask you, what is the cubed root of negative 27? I'm basically asking you, what to the third power is negative 27? You're kind of answering this question. What to the third power is negative 27? And the answer to that, of course, hopefully you know, is negative 3. And I'd have to put that in parentheses. Negative 3 to the third power is negative 27. So that means the cubed root of negative 27 is negative 3. Now, if these were all positives, if I asked you what is the cubed root of positive 27, then I'd be asking you what to the third power is positive 27, and that would be positive 3. Okay, so you can't have positives or negatives. All right, let's talk about, let's do this example here, and then we'll talk about variables after this example. So we have 54. Okay, great, but 54 is not on our list of perfect cubes. I got 1, 8, 27, 64. I don't have 54. So what we have to do is ask ourselves, are any of these numbers factors of 54? There's not that many to check. That's the thing with cubed roots. There's not going to be that many to check. Don't ask yourself what goes into 54, because it doesn't really matter if it goes into 54 unless it's a perfect cube. So yeah, 9 times 6 is 54. But I don't care, because 9 and 6 are not perfect cubes. Now, if this was a square root, then I would care, because 9 is a perfect square. So again, you're not really concerned about what goes into 54. You're concerned about what perfect cubes go into 54. And I put 1 on here to get the list started, but 1 never does anything for you. So, don't worry about it. It's not going to make it any simpler. All right, so 8, that doesn't go into 54. 27. All right, great. So 27 goes into 54. How many times? 27 times 2. So I'm going to change my 54 to 27 times 2. Now I can take the cubed root of 27. All right, I can take the cubed root of that. That guy's going to come out of the cubed root and become 3. I'm going to take the cubed root of that guy, and it's going to change him to a big old 3. And this 2, this poor 2, is left inside the cubed root because it's not a perfect cube. So he's left inside this cubed root. And that would be your final answer, 3 times the cubed root of 2. Okay? And actually, if you took your calculator and did the cubed root of 54, and you got some decimal, I'll do it on my calculator just so you can kind of check it out. And if you don't know how to do that on your calculator, all calculators are different, so it's really hard to go over something like that in a video. But if you do it right, you should end up with 3.7797 something. Oops, 7 something. Like I said, I was going to say, you could just Google how to do it on your particular calculator, how to do cubed root on TI, whatever. All right, and if I punch this one, if I punch in 3 times the cubed root of 2, I get the same exact decimal. So that's one way to check and see if you have done the correct simplification, because I haven't changed the value of the number. This number should be worth the same amount as the number I started with. I'm just changing how it's looked, how it's presented, okay? Like reducing a fraction or something. Okay, great. Let's go to the next example. Now, what do I do if there's variables in there? All right, so let's put up the next example, and then we'll talk a little bit about how we're going to deal with it. So let's say I have the cubed root of negative 56 x to the fourth y to the fifth. How do we deal with that x to the fourth, y to the fifth? We're going to deal with the 56 the same way we dealt with the 54. We're going to see if there's any perfect cubes that go into 56. I think I see one right there. 8 goes into 56, or negative 8. All right, we could use either one of those. But let's talk about these variables for a minute. I have a list of perfect cubes. That was very important to me to think about simplifying. I need to continue this list of perfect cubes with variables. So let's start with the easiest variable, which is x. What do I get when I take x to the third power? Well, that one's kind of straightforward. That's x to the third power. Okay, so x to the third power is a perfect cube because it is literally x to the third power. So if you had the cubed root of x to the third power, you'd be asking yourself, what to the third power is x to the third power? And the answer is x. Okay? Now, let's go to the next one. What if I had x squared to the third power? I'm going to create these perfect cubes by doing stuff to the third power. That's how I make perfect cubes. I take something to the third power. Just like we made these perfect cubes by taking 2 to the third, and 3 to the third, and 4 to the third. What do I do here? X squared to the third. I multiply these exponents. So x to the sixth is a perfect cube. All right? The cubed root of x to the sixth is x squared, because x squared to the third power is x to the sixth. How about this one? Next one would be x to the third, right? I'm just doing x squared, x to the third. What do I get? I multiply these exponents and I get x to the ninth. So the cubed root of x to the ninth would be x to the third. Let's go to the next one. X to the fourth. Multiply these exponents, so I get x to the 12th. So the cubed root of x to the 12th is x to the 4th, because this is asking me what to the third power is x to the 12th. And I can see the answer over here. X to the 4th power to the third power is x to the 12th. So hopefully you're seeing a pattern for perfect cubes. What do we see about the exponents for perfect cubes? They're multiples of 3. Just like the exponents for perfect squares are multiples of 2. Okay, that's a pattern. If you want to take the cubed root of these then, if you want to take the cubed root of x to the 12th, all you do is divide it by 3. All you do is divide the exponent by 3. Okay? Easy. If you know what to do, it's easy. But we look up here and I got x to the 4th and x to the 5th, or y to the 5th, and neither of those are divisible by 3. So we're going to have to talk about what to do about that. But that's what you're looking for with the exponents. You're looking to see if they are divisible by 3. So if you have something like, we're going to get to this tougher example here in a second, but if you have something like the cubed root of 27x to the 27th. Okay, I just really want to emphasize how we're going to treat these two 27s differently. The cubed root of 27 is 3, right here. 3 to the third power is 27. But if it's x to the 27th power, if it's an exponent, then I'm asking myself basically what to the third power is x to the 27th. You know what it is? It's x to the 9th, right? Because you multiply these to get 27. So to get your answer, all you have to do is divide. You take the 27 divided by 3, and you get x to the 9th. See how I treated these very differently? The 27, I take the cubed root to get 3. The x to the 27th, I divide by 3. So that's super important. You need to think about treating those two numbers differently. Okay, let's go to our example. Here we go. We got 56 over here. Let's deal with the 56. So, and actually let me do this. I'm going to do this. This is going to be a little crazy here, but I'm going to do this for this first example. You don't have to write it out like this and break it up, but this is really what you should be thinking in your mind is I'm going to treat this like 3 separate problems. So for this first example, I'm going to break it up into 3 separate problems because that's how I want you to think of it. So I'm going to deal with these separately. I have the cubed root of 56. Is there anything in my cubed root list over here that goes into 56? And yes, we said 8 or negative 8. And since there's a negative there, let's get that out of that cubed root. You want to simplify it as much as you can. So I'm going to split this 56 up into negative 8 times 7. Now I can take the cubed root of negative 8. All right, green light on that one. We can take the cubed root of negative 8. That's going to be negative 2. Now I can't take the cubed root of 7, so it's just going to stay inside. And don't forget to write this little 3, because if you don't, you have a square root. You have to write that little 3 up there. And make sure you write it up high and tucked into this little check marky thing. Otherwise, it's going to look like multiplying by 2. And you don't, it's just a little, like this guy goes together. I'll do this in orange. This is, think of this as like one symbol, a cubed root symbol. And it's all tight and goes together. Okay, let's go to the x to the 4th. So we go to our list, cubed root. Here's my list of my perfect cubes. I have x cubed, x to the 6th, x to the 9th. I don't have an x to the 4th. So I need to break up the x to the 4th into one of these, x to the 3rd, x to the 6th, x to the 9th. So basically what you do is you take your exponent, x to the 4th, and you go down to the next multiple of 3, which is going to be x to the 3rd. So what times x to the 3rd is x to the 4th is x. So I'm splitting this x to the 4th up into x to the 3rd times x. How about the y? Same thing, right? I have to go down, so it's going to be y to the 3rd. I don't go up to y to the 6th, and then y squared. Because remember, you add these exponents. 3 plus 2 is 5. So I took my y to the 5th, and I split it to y to the 3rd times y. Okay, what else gets to come out of the square root or cubed root now? That guy gets to come out, and that guy gets to come out. So the cubed root of x to the 3rd is just x. And that's going to leave poor old this guy x left inside. And this guy y squared is going to get left inside. Alright, so for the middle part we end up with that. And then the cubed root of y to the 3rd is just y. And that y squared, he gets left inside. Okay, so now to write our final answer, we're going to write it all back together in one big thing. Everybody that's on the outside of the cubed root is going to go together. So I have a 2x and a y. And everybody that's inside this cubed root is going to go together. So I have a 7 and an x and a y squared. Now my next example, I'm not going to split it up into 3 different pieces. We're just going to kind of keep it together and work with it. But this is how we want to think of it. Okay, we want to think of dealing with each of these separately and then pulling out what factor we can from each of those separate factors. All right, let's try another one. I got a few more examples here, so let's kind of go through these now that we got the setup. And I would encourage you to pause the video and try this next one if you feel like you're ready. Let's see, let's do this one. The opposite of the cubed root of negative 216 a to the 12th. That's not a b, that's a 16. Does that look like a 6? A to the 12th, b to the 6th, and c to the 9th. Interesting. Okay, so take a shot at that. All right, so let's start with the 216. Now that number's ringing some bells for me. Look, I've got 1, 8, 27, and 64. I don't think any of those go into 216, but I think 216 is 6 times 6 times 6. I think it is. Yeah, it is. Okay, so if I would have continued this list here, 216 is 6 to the 3rd power. So that's a perfect cube already. I don't have to break it up. That's just flat on my list. He's going to come out. A to the 12th. Look at that, x to the 12th, all right? As long as this exponent right here is divisible by 3, it's already a perfect cube. So that's a perfect cube. 6 is divisible by 3, so that's a perfect cube. 9 is divisible by 3, so that's a perfect cube. You probably thought, oh, it can't be that easy. I must be missing something. All right, so I have negative 216, so this negative is going to come down here, right there. But the cubed root of negative 216 is negative 6, so that's going to give me another negative there. I'm going to have two negatives, which I'm going to change to a positive. And then a, 12 divided by 3 is 4. Remember, just divide the exponents. 6 divided by 3 is 2, and 9 divided by 3 is 3, and then we'll change that, those two negatives into a positive, and that is the answer. Oopsie, that should be a C. Okay, that one was kind of easy because we had all perfect cubes. They're not all going to be that easy. I'm sure you're thinking they can't all be that easy. Okay, let's try another one. There's that one. Okay, what do we got left here? Okay, let's get rid of this. Here's a good one. Well, this one's not too bad either, as far as the exponents go. Okay, cubed root. We'll make this a little interesting. We'll make the coefficient a little interesting. 1 over 1,000. 1/1000th. X to the 27th. Z to the 18th. All right, pause the video and give that a try. Okay, so 1 over 1,000. Well, 1,000 is in my list and 1 is in my list. So remember, the way you multiply fractions is to multiply all the numerators and multiply all the denominators. So what times itself 3 times, or what cubed would be 1/1000th? That's basically what we're asking ourselves over here. And you just look at the numerator and denominator separately. All right, 1 cubed is 1, and 10 cubed is 1,000, so it's 1/10. The cubed root of 1,000 is 1/10. That's a perfect cube right there, and that's just going to come out. Boom. Again, we kind of lucked out here because we have these exponents are divisible by 3. So all you're doing is 27 divided by 3, and that's 9. Remember, you can only do that with the exponents. So that's x to the 9th, and then 18 can be divided by 3, so that's z to the 6th, and that is it. That is the answer. That's all there is to it. Okay, so that's pretty much it for cubed roots. Maybe we should try one more where these exponents are not so nice. Let's just say you have the cubed root of x to the 7th, y to the, how about 17? Okay, you want to try that one? Pause the video. Okay, so remember, we need to take 7 divided by 3. So that doesn't work, but the next smallest one down, the next number smaller than 7 that I can divide by 3 would be 6. So I'm just going to split this up to 6 and 1. That'll give me 7. And then the 17, let's see, 17 divided by 3 doesn't work. Let's see, how about 15? That would be the next smallest one. And then that would leave me y squared, because 2 plus 15 is 17. So now I can take the square root of this and the square root of that by dividing the exponent divided by, this is called the index, divided by the 3. So 6 divided by 3 is 2, so that gives me an x squared, and 15 divided by 3 is 5. And these poor fellows are stuck inside the cubed root. They do not get out. The x and the y squared. Again, make sure this cubed root, this little 3 cubed root is really tucked up in there so it doesn't look like it's attached to anything else. And that would be the answer for that. That would be it. Okay? So you can extend this idea to all different kinds of indexes, although you won't see it very much. You could even do something crazy like the 9th root of x to the 21st. So you need to do 21 divided by 9. Well, I can't divide 21 by 9. Let's see, what could I divide by 9 that's smaller than 21? That would be 18, right? And as close to that as possible. So then I'd need x to the third to add up to be 21. Now I can take the 9th root of x to the 18th by dividing 18 by 9, which gives me 2. And then this guy, he gets to stay inside the 9th root. Again, tuck that 9 up in there. And that would be your final answer. A little weird. You won't see that too often, but that's how you would treat it, no matter what this index is when you're dealing with exponents. Well, I hope that helped, and good luck with your cube roots.